Hello. In today's lesson, we're going to take a look at the essential question of why do solids, liquids, and gases behave the way they do? And the principle that governs why solids, liquids, and gases behave the way they do is the kinetic molecular theory. This gives us an understanding of why solids behave as solids, liquids as liquids, and gases as gases. And a lot of this can be seen because the types of atoms that are present, or the composition of the substance, and their arrangement or their structure, this is what determines the chemical and physical properties of matter. Okay, so all of the properties something has is all attributed to the structure of the atoms and the molecules and the composition, what they're made up of. And what kinetic molecular theory attempts to do is describes the behavior of matter in terms of the particles of the motion in motion. So we know that particles such as molecules and atoms, they move. So the term kinetic means to move, and objects that are moving or in motion, they have kinetic energy. Now, there are certain assumptions that are made to give us an understanding. So we're going to take a look at some of the assumptions that are made for gases, and KMT is short for kinetic molecular theory. Now, the assumptions that are made have to do with the particle size, the particle motion, and the particle energy. And the assumptions that are made regarding the particle size are that the gases that are made of small particles are separated by empty space. So in between these particles is space. And the volume of the particles, or the amount of space of the particles, is much less than the volume of the empty space. Also, gas particles, they have no significant attractive or repulsive forces because they're far apart. So in other words, because gas molecules are so spread apart, the attractive and repulsive forces between them are insignificant. There's just so much distance in between them. Now, in regards to particle motion, we assume that gas particles are in constant random motion. So these particles are just moving all over the place. Also, the particles, they move in a straight line until they collide. So those particles are pretty much going straight in all sorts of directions until they hit each other. And the collisions, we describe the collisions as being elastic. In other words, there's no energy loss. Okay, the energy is just transferred from one to the other. When they collide, the energy from one goes to the other. Also, the mass and the velocity is what determines the kinetic energy. So how massive something is and how fast it's moving tells you its kinetic energy. And also, just as a reminder, temperature is measuring the average kinetic energy of the particles. Now, we have to go over a couple of terms in order to get an understanding of kinetic molecular theory. So I'm going to define some constructs related to this, and one of them being pressure. So pressure is measured as the force per unit area. So how much force something is exerting on a certain area of the substance. And gas particles, they exert force when they collide with each other, and when they collide with the walls of whatever container that they're in. Okay, so you need to be familiar with that. And also, you need to be familiar with air pressure. So air pressure, you have to know that the atmosphere, the gases in the air, they also exert actually a lot of pressure. And that pressure is going to vary depending on the altitude, how high something is. So the higher up you go, there's less air pressure, which is why sometimes you have that sensation if you've ever been on an airplane and you feel your ears popping. That has to do with the fact that there's less air pressure the higher up the airplane is. Or if you ever gone hiking in the mountains or stuff like that, the higher up you go, the less air pressure there is. And there's some instruments that are used to measure air pressure, such as barometers and manometers. Okay, and you also need to be familiar with some units associated with pressure. We typically use kilopascals, or short as kp, or pascals. We use sometimes millimeters of mercury, so mmHg. That's also used to measure pressure. We also use the units atmospheres, which we abbreviate ATM. That measures how much pressure there is. Sometimes we can use also something known as torr. You don't really see that as much, but we use torr. We use bar, and sometimes we use pounds per square inch, or PSI. Now, typically in chemistry, we'll use kilopascals, atmospheres, that type of thing. And we should know that, like, on Earth, we define standard temperature and pressure, or standard STP for short, standard temperature and pressure. The standard pressure is defined as 1 atmosphere, ATM, which is equal to 101.3 kilopascals, which is equal to 760 millimeters of mercury, which is equal to 760 torr, which is equal to 14.7 psi, which is equal to 1.01 bar. Now, the main ones you have to know, which is typically used in a chemistry course, is 1 atmosphere and 101.3 kilopascals. Okay. Now, you also have to be familiar with certain forces of attraction that exist between molecules and within molecules. Now, intra, the prefix intra means within. The prefix inter means between. So if we're talking about, intramolecular forces, we're talking about forces that are within the substance, within the atom. And some of these intramolecular forces, you may recall, are covalent bonds, when the atoms share electrons, ionic bonds, when there's a transfer of electrons, and metallic bonds, when there's a sea of electrons in metals. So all of these three are intramolecular forces, which means that there are forces of attractions within the atoms. As opposed to intermolecular forces, which means between substances. So from molecule to molecule, there are also forces of attraction between those. And some examples of intermolecular forces include dispersion forces, dipole-dipole forces, and hydrogen bonds. Okay, so the first intermolecular force, dispersion forces, these are weak forces, and they're temporary. They form from temporary shifts in the density of electron clouds. Sometimes they are also referred to as London forces. So these are basically very weak forces between two substances. In this example, between two helium atoms. There's also going to be some weak forces of attraction between those two atoms there. The second intermolecular force, dipole-dipole forces. These are forces that they're attractions between oppositely charged regions of polar molecules. So you have a polar molecule like this, HCl, or hydrochloric acid. This symbol here means the H is slightly positive, and this Cl means that it's slightly negative. And then you have another substance here of hydrochloric acid, another group of them. This is slightly positive and slightly negative. So the dipole-dipole forces are going to be the forces of attraction between each group of hydrochloric substances, for the molecules. Not technically a molecule, but you can think of it as a molecule between them. And then the last intermolecular force is hydrogen bonding. And a hydrogen bond is a dipole-dipole attraction that occurs between molecules that have hydrogen atom to a small, highly electronegative atom with at least one lone pair. Now, it sounds confusing. No, it sounds confusing. I'm going to try to clear it up. But hydrogen bonding is a very, very important bond because that's the reason why water is a very unusual substance. Okay? So these hydrogen bonds account for why water has an unusually high boiling point compared to other substances. And this is what this table down here is trying to demonstrate, that you have these four substances, ethane, and this is its structure for it, methane, that's the structure, methanol, its structure, and water. So if you look at ethane, it has a boiling point of negative 88.6 degrees Celsius, which is very low. Methane has a boiling point of negative 161.5 degrees Celsius, which is also very low. Methanol, another substance, has a boiling point of 64.6 degrees Celsius. Gets to be a little higher. And then you have water, okay, which is similar in structure to some of these other things, but water has a boiling point of 100 degrees Celsius. So it's kind of weird that water is going to have such a high boiling point compared to some of these other substances. And the reason why is because of these hydrogen bonds. And this picture over here is trying to demonstrate. This is one water molecule, and then this is another water molecule. And then between the water molecules, there's an intermolecular force between this hydrogen and this water, and this oxygen and this water. It forms an attractive force between them, and because of that, water has an unusually high boiling point. Okay, couple more things. We're going to take a look at some principles behind liquids, because kinetic molecular theory applies to liquids as well. We know that liquids take the shape of their container. Liquids tend to be much denser than gases. Liquids are considered incompressible, so you can't press liquids down, unlike gases, which you can compress. Liquids and gases are considered fluids because they can flow, and viscosity is something that measures the resistance of a liquid to flow. So you can think of it like if you ever tried pouring honey or syrup, you notice how slowly it pours. That's because of its viscosity, as opposed to water, which is not as viscous as honey. And then surface tension is a measure of the inward pull by particles in the interior. So it has to do with these forces at the surface of the liquid. And then we're also going to take a look at how kinetic molecular theory applies to solids. We know that solids have a definite shape and definite volume. They tend to be more dense than liquids and gases. There are different types of solids. There are crystalline solids, and those are solids whose atoms, ions, or molecules are arranged in a pattern. So like salt is a crystalline solid. And then you have some other substances called allotropes. Allotropes are elements that exist in different forms at the same state. So for example, diamonds, graphite that you can find like in pencils, and something called a Buckminster fullerene. All of those three things are the same thing. They're all carbon, but the structure is very different. Okay, so those are allotropes. And these diagrams here are trying to represent the structures. So in diamond, which is all carbon, this is the structure of the carbon in diamond. You see it here. And then in carbon in a Buckminster fullerene, here's how it's structured, like a ball here. And then the carbon in graphite is structured in layers here. So those are allotropes. And then the last thing, we have amorphous solids, which are solids whose particles are not arranged in any regular pattern. So like something like obsidian, which is an igneous rock, we would describe that as an amorphous solid. Okay, so we're going to stop here. I'm going to give you guys a couple of problems that relate to kinetic molecular theory. Thanks.